This lecture is in continuation with the lecture series of linear algebra. Topics covering will be row reductions, Echelon forms, uniqueness of reduced Echelon form, statement theorem only, pivot positions and pivot columns, and questions based on the same. So first of all, row reduction and Echelon forms. The definition: a rectangular matrix is in Echelon form if it has the following three properties. Matrix will be in the Echelon form if it has these three properties. First of all non-zero rows are above any rows of all zeros. Any rows of all zero means if there is any zero row, it would be at the last. All the non-zero rows will be above it. Second one is each leading entry of a row is in a column to the right of the leading entry of the row above it. Each leading entry of a row is in a column to the right of the leading entry of the row above it, means once you have achieved a leading entry in a particular row, in the next row it would be to the right of it. The third one is all entries in a column below a leading entries are 0. Once you have achieved a leading entry, all the entries below it would be 0. So these are the example of Echelon forms. Suppose this is a matrix of 4 by 5 matrix. Square I am representing with a leading entry. It can take any non-zero values in Echelon form. And elements below it would be 0. Next leading entry of the row of the next row would be to the right of the first row. Star is the element which can take any value including 0 or non-zero. It can take 0 also, it can take non-zero also. We don't worry about the star entries. We are worried about only the square entries, which are the leading entries, and elements below it should be 0. This is row Echelon form. In short we say REF. So there is another example of 5 by 7, so that you can get an idea of how to make Echelon form. It may happen the first column is free from leading entry. The leading entries start with the second column. Elements below leading entry would be 0, and next leading entry would be to the right of it. It may take the next column or it may take the further far column, but it would be to the right. Right? So next is row reduced Echelon form, RREF. If a matrix is already in Echelon form and satisfy the two more additional conditions, then it is in the row reduced Echelon form. So three conditions already being satisfied by the matrix, which is already in the Echelon form, and now we are converting it into the row reduced Echelon form by satisfying two more conditions. The first one is leading entry in each non-zero row is 1. The second one is each leading entry 1 is the only non-zero entry in its column. Means the leading entry which you have achieved in before Echelon form, that would be preferably 1 in row reduced Echelon form, and all the elements above and below the leading entry should be 0. These are the example of row reduced Echelon form. Any 0 row, if it contains, will be at the last. Leading entries of the next row will be to the right of the above row, and elements above and below the leading entry should be 0. So next is theorem. Theorem is about the uniqueness of reduced Echelon form. Each matrix, there is only statement of this theorem. Each matrix is row equivalent to one and only one reduced Echelon matrix. Means row reduced Echelon matrix is unique. Suppose there is a matrix A. By row operation, we convert it into Echelon form. Echelon form can be many. because every student might be getting a different Echelon form with a different leading entry. Suppose someone is getting leading entry as 2, someone is getting leading entry as 4. So leading entry can take any value. So Echelon form are many, but when you convert it into reduced Echelon form, leading entry becomes 1. Leading entry should be 1 in reduced Echelon form, so that's why reduced Echelon form is unique. But the thing is, the point of thought is leading positions are same in both the forms, whether it is Echelon or it is reduced Echelon, and those leading positions are called pivot positions. So that is the next topic, pivot position. A pivot position in a matrix A is a location in A that corresponds to a leading entry, basically. That corresponds to a leading entry 1 in the reduced Echelon form. So whichever position is corresponding to a leading entry, that position is called pivot position. And the column which contains the pivot position is called the pivot column. Right? It would be more clear with the question. So next I'm discussing the question based on the same. Suppose there is a matrix A with these entries 1, 2, 3, 4, 4, 5, 6, 7, 6, 7, 8, 9. We need to find pivot position and pivot columns by reducing the matrix into Echelon first and then reduced Echelon form. First we need to convert it into Echelon and then reduced Echelon form, and to find the pivot position and pivot columns. So to solve this, I'm writing the matrix again. Since the very first entry is 1 and it is non-zero, so this is our leading entry for this row, and that is why this is called pivot position, and first column contains pivot position, so first column is the pivot column. We need to create zeros below the pivot. Below the pivot we need to create zeros, so we need to apply operation likewise. R2 tends to R2 minus 4 times R1, R3 tends to R3 minus 6 times R1. Operations are like, we need to create the zeros below the pivot and we need to take the help of the pivot. Right? So there is no change in the first row. Second and third row is changed as per the operation. In next you will see the A22 position is pivot position because it is non-zero. And since the second column contains pivot position, so second column right now is pivot column. And we need to take the help of pivot position to make the element below it 0. So R3 tends to R3 minus 5 by 3 R2. For these you take the rough part to write R3 column minus 5 plus 3 into 5 by 3 comes out as 0. Likewise, the third position in the last row and fourth position in the last row is also 0. So this is actually in the Echelon form. Why? Because it's satisfying the properties of Echelon forms. Leading entries are A11 and A22, so these are the pivot positions, and pivot columns are 1 and 2. To further reduce this matrix into reduced Echelon form, we need to make the leading entry as 1, and we need to make the element above also and below also the leading entry should be 0. So first operation is R2 tends to R2 divided by minus 3 to make the leading entry 1. And next operation is R1 tends to R1 minus 2 times R2 to make the element above the leading entry as 0. So now this is as row reduced Echelon form, satisfying all the 5 properties of row reduced Echelon form.